show a quick.
I'll just sorry to introduce before you start. What's your name?
Johnny Anderson. Anoq is on in public.
Yeah. Okay. On a project called CeX3D, and it's a 3D application using SML. Yes.
Thank you. This is a 3D model generated by the program CeX3D and Anoq, and it's still messy and has holes and stuff. It's work in progress. There are actually slightly better models nowadays and on a good day. This viewer is not mine. It's not written in standard ML, but the model is generated in standard ML, and there are quite a lot of polygons, like between 1 and 2 million polygons. It's probably a bit blurry here. I'll try. This I've been able to do like for some time by now. But I'll show you something I just made this week. If we can just find a model here. This one. Yeah. This bit hard to navigate, and it's also, let's see if we get my lights on this. Yeah. And we don't want the wireframe. And maybe we want it. It's hard to navigate, I tell you. It's supposed to be a castle, and then let's see here. If you can see the model here, it's really not convincing, but and the light again. It's simply too dark, but maybe you can see the tower. The shape of the tower is rounded here, but it's hard to see. Let's just go to the slides. And I didn't show you that this actually comes from, this was reconstructed automatically from 3 images, both of these 2 models. And I'm not going to try to show you the images, but anyway. So that was hopefully sort of a demo. And well, the reconstruction, back then it took like 2 or 3 hours. Now it takes more like 1 hour to reconstruct this, like 1.2 million. And the small model, it takes like, it's a little faster, maybe slightly more than half an hour. But still, there's lots of room for improvement. And yeah, the key word here in this program is that it reconstructs the model automatically without any prior camera calibration. That's actually the hard part. And it's, especially the radial distortion of the lens, that's actually still the primary point of failure. And the program is written in standard ML, but now I've tried to go through some of the technology that I use in CeX3D Inverse in particular. I'm trying to show you how to do efficient image processing. So it's a little bit of tutorial here. I define this type as a frame buffer area, the start address, and the number of bytes to skip at each line of scan, at each scan line, and the number of bytes to skip at each pixel, and the region of the image area. And this is a primary data structure that I use for like handling images in general, and also, as we see, rendering images efficiently on the screen. This function, I'm not going to show you the implementation, but it folds over an image buffer. This is a schematic of how it folds over the pixels. It's like between each scan line, the fy function is called, and folds an alpha value initially. It's like fold left initially a alpha and returning the final value folded over the lines. And at the start of each line, we convert to a beta. And at the end of each line, so there's no at the end of each line. And between each pixel, there's an fx folds through that function. And each pixel we apply a function given the frame buffer address and the beta value we accumulate. And C is just anything we don't care about that, it's not used. So it could be unit or whatever. And here is an example using that. And now we can already at slide 3, we can do a color gradient. It just interpolates an integer through the scan lines downward, adding 100 for every scan line. And at the start of each line, we make an RGB color, starting with the interpolated value for R, and starting at 0 for green, and this value for blue. And these integers are integers in the range, the colors, each color channel is integer in the range 2 to 255, scaled by 256, so to make some kind of fixed point integer math. And for each pixel we add 100 to green and subtract 100 from blue. And when we run this through apply, starting with 0 for the color gradient down, and we get this color gradient. The only thing here I haven't defined is the pixel apply function, but I have 3 of those later. And the FB area, it was the data, this record from before. That I'll also define later, an instance of this. And here's another example of, you could also make a more elaborate traversal function. I'm not going to go through that. That obviously falls through like buckets of line and pixels and stuff like that. But that's actually basically the main function for a scanline renderer. So I'm not going to go through that. Let's see. Oh, I think I skipped this slide. Oh, yeah. Yeah, okay. The performance of the function from the previous slide, I've tried actually writing a scanline renderer directly by doing everything inline, and then later on abstracting out that function you saw. And I saw no difference in performance when using with the 2007 version of Milton. So I think take-home message here is the whole program optimization of Milton. It actually makes this kind of abstraction that you can make this kind of fold function over a frame buffer. It's essentially cost-free. So I think that's a good message. And actually I think that was an earlier version of Milton than 2001, 2000. And when I later upgraded Milton, it got even faster. So I'm still using the abstraction, of course. So Milton's performance, I think it's really good here. Now the right pixel functions. This is first a simple function, just writing a 32-bit value to the frame buffer, right written in C, exported to standard ML by Milton's formal foreign function interface. Yeah, it's just a simple way. Another way we could do it here is that we directly map the RGB value, this red, green, blue color values, and do the bit shifting so that we pack it as a RGB value here. And remember again that the scale for 256, so that's why we're not like shifting this value, for instance. It has to be in this place, this bit place. So we just zero out here the lower 8 bits, and yeah, the binding to standard ML. And alternatively, we could do the pixel packing in standard ML, and it looks like this, the same bit shifting as here. And then we need another function to combine it. We have the 3 pixel apply function here for the gradient example. One that calls the C function directly, that makes the bit shifting in C. One where I write just the 32-bit value and then do the bit shifting in standard ML, the function on the previous slide. And then here, using Milton's pointer interface. And it's a little inefficient pointer arithmetic here because I couldn't make an on-site custom address. I had to add it to another pointer. But anyway, it works. It's still a bit shifting in standard ML. See, and then, okay, we need to create an image buffer. The slides will be available online. You can study this. It's like to convert, to find the start address of an XY position and to compute the end of line skipping. I'm using the SDL library that uses something called the pitch, which is like the bytes for each scanline, and I use the bytes at the end of each scanline after the last pixel. That is usually, not necessarily 0 for alignment reasons. So, but anyway, this is how to construct that. Of area from the earlier slide. And here we can, this is rendering one frame using the SDL library. We need to lock the surface to get direct access. We get the width and height, and then we use the function from the previous slide here to create a frame buffer area. And then we can do the rendering here, and that could be the gradient example I showed. And for each frame we do the SDL flip is basically for double buffering, where you switch between two buffers. So you render it. So this is rendering one frame efficiently. And here's some more STL stuff for opening an STL surface. And I've got an example where I'm like a simple performance evaluation where I'm rendering 1,000 frames of this gradient and timing use time.now in standard ML basis library. And here are a few things about the STL bindings. You can find STL here. Oh, sorry. And my bindings are pretty old. And the bindings I show here in the slides are actually a bit newer than what you can find. So there are a few caveats here. The naming convention has changed to STL underscore quick, and you use the old Milton FFI, so you need to replace prim by import. And the interface, the old one, is less complete and stuff like that. And the sound routines are buggy, so don't use those. But anyway, and here's some performance. I have first one setup, one computer, my stationary at home from 2008. And here are all the information you need to know. It takes like 3-point-something seconds to compile. And it actually becomes slightly more than 10,000 lines of code, but this is due to hardcore version's repository included. It's just this code I've shown you, but it's just dependencies. But it's quite fast compilation for this. But of course, Milton's dead code elimination removes most of it. And timings, to render 1,000 frames, it took around 9 seconds. The time varying by some milliseconds. And that was for all three examples, all three right pixel functions that I tried. So it's hard to say on this computer which is fastest. And I can say that if I'm also using, I had a slide just before STL flip, I had an update rect function. That if you do that, if you don't use double buffering, you need to do this, and then the time actually increases to almost twice as much. And that's supposed to be hardware accelerated. So I think my rendering is pretty much as fast as the hardware accelerated updating of the screen. So, well, copying from a software buffer. So I think it's efficient. And well, it gives 111 approximately frames per second, 40 megapixels per second. Because there are, so this is here. And this is without graphics card acceleration. On another machine, it's a laptop, it's this laptop. It takes longer to compile, but it's actually faster to render. And I think it's because I have better graphics drivers enabled here. And now the three different functions actually have different timings as well. They didn't on the other machine. I don't know why actually. The one where I do RGB packing in C, it takes 7.6 seconds roughly for 1,000 frames. And if I do the RGB packing in ML, it takes 8.2 seconds. And then I just wrote the 32-bit value in C. So this is probably not good advertising for bit shifting in standard ML. I don't know. But if I use Milton pointer, then I actually get time down to 2.4 seconds. And this is like 3 to 4 times faster, and I have no clue why. But apparently, sometimes this is a good thing. And I tried it like several times. I didn't do systematic averaging over 100 runs, but it's quite systematic. This I tried several times. And so here the frame rate is from 120 frames per second to 415 frames per second. 43 megapixels per second to 150 megapixels per second. And again, without graphics card acceleration. I think that's pretty fast rendering. Yeah, suggested improvements. I would actually suggest improving Milton's garbage collection, but the disclaimer here is I'm using the 2007 version. I don't know if it has improved since then. But I have seen examples where I get significantly more garbage collection forces, and they're quite slow, and it actually hurts performance quite a bit. And this was just by an example of an optimization where I did in-place editing in-place modification of large arrays rather than copying them functionally. That actually gave a significant improvement. And also, I would say the latest version of Milton seems to support building dynamic libraries, and I think this is good news. I think it's important. Also, for other standard ML compilers, this is important. Like Alan's FlexDLL in OCaml, it's a good thing. Another slide here. Some of the technology written at hardcore processing, also for the 3D reconstruction application I showed, it's like there are several numerical algorithms that I wrote from scratch, the standard ML matrix, and all kind of stuff. And the second order code program is quite hard. I have several like 3D renderers following RenderMine API, GUI toolkit, GUI builder, efficient parser and streaming I/O models for rapidly building applications. I have compiler technology. Most of these were DQ project student projects. And actually, I have a statically tag-free 2-generation COP and MARC region garbage collector based on the 2008 image paper. And I would actually suggest later on that this might be interesting to incorporate into Milton. But, let's see. And now, for the program where the demo was a bit, I just showed you the model, the program that generated the model. It consists of like 186,000 lines of standard ML code. When I submitted the abstract, it was around 160-something thousand, so I think I've written 20,000 lines of code in the past 3 months. I must have been busy. Feels that way. And approximately 10 small C functions, like the write functions I showed you earlier. And it takes 57 seconds to compile this with around 1 GB peak memory usage. Using the same computer from the performance value. That was the first computer, not the laptop, not this one, the stationary. And we have standard ML's type space if it crashes. There are not many places it can go wrong. It can go out of memory, that's quite frequent. Or it could be bugs in the compiler, or bugs in SDL, or illegal calls to SDL, or mostly writing outside the image buffer. But the frame buffer traversal function I showed you, that greatly helps actually removing the risk of writing outside those buffers. So that's convenient. Some plans, other plans of commercial products from hardcore processing. The commercial standard ML library product that I'm considering to release some of those numerical algorithms that I mentioned earlier. Anoq SML basis library. It was submitted to earlier ML workshops, but it needs further work, and it's also another thing that could be released, the commercial version of the GUI toolkit. And then I have planned 4 steps in making standard ML more famous. One is release of this Anoq SML basis library. It could be possibly an extension to the SML basis library. Release of the commercial library product, and publication of a book, real life programming in standard ML CeX3D. This is my programming language. Step 4, I cannot tell you that. You have to wait and see. And yeah, when it's all coming, if you can finance it, we can deliver. That's hardcore processing message. And a couple of suggestions for projects, like my master's thesis about the garbage collector. If incorporating that into Milton is interesting to anyone with commercial financing opportunities, I would be interested in doing that. And otherwise, if you can purchase several GUI toolkits or libraries, maybe I can accelerate those plans. Otherwise, you will have to wait with these things being released until that time. But those are some of the plans. And for this talk, yes, I got the 2 slides with reviewer questions, reviewer number 4. Why did you choose standard ML? Well, I settled on using it in 1997, 1 year before starting at DQ, so my bias is not from there. Then I became convinced that it was a good language and one of the very few standardized and stable languages. That's, I think that's important. Good communities. The Milton mailing list is good, and I used Combine ML in the old days. Good bad things about standard ML for such a product. I can keep building code upon code more than 10 years old without the language changing, and the language itself is good. Particularly for abstracting things such like that algorithms and modules that only needs often to be written once, like the traversal functions I showed. And bad, I have to write everything from scratch. There's not really much available, but I'm making sold by products, so I'm trying to make a business out of that as well. So are there any standard ML specific language features not found in other languages that are particularly useful? Strict evaluation, I found that it gives predictable and efficient performance. And I generally like exceptions and arrays, and imperative arrays very much. And I use free references, and I think the interoperability with C is important, like for the right functions. interoperability with languages I actually don't use very much. As you saw, I could do mostly, except opening a frame buffer could be done like without any interoperability. So I just need to read images from the file, reconstruct a 3D model, generate a huge 3D model. I actually don't need to interoperate with anything except for a few lines for writing to a frame buffer. So, but if you need 3D rendering and movie, then of course you need something else. SDL. And I don't think I have time to enable the other laptop and show demos, but you can find these slides online if you didn't catch it all, if you want to try to implement it on your own. And I have actually several flyers for the product that the demo was a bit flaky. I can put them on the table if there are no commercial conflicting interests in the workshop, if you like. And yeah, I don't know if there are any questions.